All right, so I think a good way to start out today is to first go over some of the stuff we talked about last week, just as a refresher. So, um, right here I have a little bit of a line, 3 hashes on it. This is in reference to one of the things we were talking about last week. Does anyone know what the hashes refer to? Uh, Specifically, what kinds of compounds I might put marked out here?
Gases.
Water.
Water. Okay, water for the middle one. Let us say. Let's say that
Oh, isn't
on
that
the yeah,
hydroxide and hydrogen?
say that again. I need to turn up my volume a little bit. So
Oh, sorry.
yeah,
Isn't it hydroxide and hydrogen?
hydroxide, yes. Hydrogen,
Hydronium.
hydronium, yes.
Oh,
So H3O plus, basically just water and hydrogen, or a hydrogen ion put together. So I'm gonna mark this right side with H3O plus, and then I'll mark this left side with OH minus. And then now that gives us an acid-base ring. So in the middle, we have neutral water right here. And then here we have the start of strong bases. This is the interface between strong and weak bases. I'm gonna erase this K and Ka real quick. Give me a sec. All right. And yeah, so let me just put down a few more acids. I'm just gonna kind of set up what we were talking about last time. I'm just gonna put a few examples here and there. A good exercise, I think, is to see if you're able to identify some of these compounds by name.
Ammonium. Oh, shoot.
Say again, Amos?
What? You just had ammonia on there.
Yeah, ammonium there. For the weak acid here, do we know the name of that?
The
CH3.
CH3 one.
Yeah,
Um.
Something silic acid. That's my guess.
salicylic acid. Uh, that is a pretty good guess because you see the carboxyl, the acid group. This right here, COOH. That is a good thing to recognize, and you
Does
know
it have
that's an
something to
acid.
do with like acetate? Because acetate also has CH.
All right, Larry here
Acetic
mentioned.
acid.
Yes, acetic acid. Larry's also got it with vinegar. That is, acetic acid is what is in vinegar. Usually, maybe like a 5%, something like that. I don't know that exact number, but yes, it's in vinegar. Um, what else? HCl. That's just hydrochloric acid. And remember, okay, actually, let me put it this way. This right here, the KOH. There's a problem with it being right here. And do you guys remember this detail about the KOH?
Wait,
I
was
put
it
it,
about telling how strong bases are?
yeah, I put it behind OH minus, but that's technically incorrect. Where should it actually be? Any idea? Before it, Larry says before it. Not exactly. Usually, especially this, I think mainly applies if you're in water. Um, this should be right on OH minus because KOH essentially when you dissolve in water, it does the usual ionic thing where it separates into K plus and OH minus. So essentially it just adds OH minus directly. It doesn't do it like for example, HCl is its own thing where it dissociates at a certain rate. KOH doesn't so much have that in water. It just actually just provides OH minus directly. So um so it would be approximately on there. Of course, there will be a way to determine between whether something is strong base, what bases are stronger, so on and so forth. For example, I'm gonna put down, let me put down MgOH2. So the thing with MgOH2 is that it's gonna be not as strong of a base compared to KOH. And that's actually because MgOH2 is not very soluble in water. It doesn't dissolve very well. And essentially, you know how KOH you put it in water, it separates to K plus and OH minus. MgOH2 should theoretically separate to Mg2 plus and 2 OH minuses, but it doesn't do that very readily. That's because the bonding is strong. Then here we get into ionic compound discussion. But suffice it to say, it doesn't separate so readily in water, and therefore you're not going to be providing a lot of OH minus. So therefore, at least in water, KOH is going to be a stronger base than MgOH2 simply because MgOH2 doesn't separate so well. And that's essentially the main point with acids and bases, right? For example, if acetic acid lost its H plus very, very readily, then it would be strong, but it doesn't do that. And there's a variety of reasons why. There's energetics, there's bonding, and both of those are very connected. But it doesn't do that. Like the polarity is not as great. Which brings me to my next point about we were rating different acids and bases based on their strengths, and I'm aligning HBr and HI here. So this indicates HCl is the weakest of the strong acids here, and then the other ones are stronger. Why is that? Perhaps anyone remember?
Larger size.
Larger size, and that means more polarizable. So larger size, that means larger area across which to spread negative charge, and therefore it's going to be more stable in a separated form. If that separated form is more stable, it's going to be lower energy. Therefore, the overall equilibrium is going to be more favorable for it to separate. Therefore, more acidic. Basically, in water, another way to think about it is that in water, HCl, HBr, and HI, they separate almost entirely. 99.99% of every HCl molecule will separate in water when you dissolve it. Therefore, that's a lot of acid you're putting in. But on the relative scale, HI is actually going to separate more. So, for instance, let us say, I'm making another bar right here. Let us say we have a solution, well, not a solution. Let's say we have acetic acid. So just, you know how we might have like acetic acid in water? Let's say we just have acetic acid, or 100% acetic acid, or at least as close as we can get to that. Just imagine acetic acid liquid. So not acetic acid aqueous, acetic acid liquid. Now let's put HCl and HBr and an HI in there. What's going to happen is that our new center, at least for this particular solution, you may consider that as CH3COOH. This side right here is a little harder to say. This side right here is just going to be the, it's just going to be CH3COO minus. The thing is, the equivalent of H3O plus doesn't really exist for acetic acid. It's just so unstable that it kind of doesn't work. It probably would be CH3. Actually, what do you guys think? Well, if you had a conjugate acid of CH3COOH, what would be its formula? If we think back to what we talked about with adding an H plus.
CH4COO2 minus.
Think about that. Where'd you get 2 minus? Because if we're talking about conjugate acid, we're going to be adding a plus. Say again, Amos.
Wouldn't it be 2 plus or 1 plus?
1 plus, yes. How many H's?
2 H's at the end.
At the end. All right. Larry's asking a question. Why is CH3COOH written the way it is and not C2H4O2? Very good question. No, that's not a dumb question at all. That's a very good question. C2H4O2. I'm typing right now. You guys, can you guys see this, by the way, what I'm typing?
Yes, yes.
Oh, you can. That's good. I know that sometimes you can't until I'm finished typing. But anyway, these are the same compounds. So if I were to say C2H4O2, that would also be acetic acid. Most people would recognize that acetic acid right away. And that would be a very fair way of representing it. I could also write HC2H3O2. That's also acetic acid. But if I were to say CHCH3OHO or something like that, that's a completely different compound. Oh, that's actually not a compound. And let me explain what's going on here. So the one Larry brought up, which is C2H4O2, this is what's called a molecular formula. It basically just illustrates what elements you have and how many you have very robustly. It's just right there. It doesn't show anything about structure. It doesn't show anything about the different parts to this compound, nothing about that. But it gives you what elements are there. So that's the point of it. This one right here, HC2H3O2, what this is illustrating is that it's highlighting the ion. It's highlighting the C2H3O2 minus part. It's saying there's this negatively charged ion here, and it has an H attached to it. I'm not telling you about structure though. Like HC2H3O2 doesn't tell you anything about structure, but it tells you that there's this ion that exists here. It makes it more clear. All right, and then we get to the most specific, which is CH3COOH. And from here, now you can straight up draw a diagram of this. So I'm gonna try to do that right now. Right now I'm using a different iPad, so that's why I'm doing a lot of typing and boxing instead of actual writing, because writing means I'll have to use my finger. But I'm gonna do it real quick just to illustrate this point. C, H, 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 C, O, O, H. Using CH3COOH, I now know how the molecule looks like. I know its structure, or at least I can predict its structure. That's something you can't have with other formulas. So like C2H4O2, it doesn't tell you this information, but it's still another way of saying acetic acid. So they're both ways of saying acetic acid, but one just gives you a little more information. So if you're doing organic chemistry, you're going to see CH3COOH more often, whereas inorganic, maybe you'll see C2H4O2 occasionally. So yeah, that's what I have to say. Anyway, getting back to this question, if I were to want to find the conjugate acid of CH3COOH, what do you guys think that'd be? Remember, it's just adding an H plus to it.
CH4COOH plus.
Yeah, that's one way of representing it. It would not be fully correct because hold up, let me illustrate why. Because I put my diagram right back there. The way you said it there indicates that there's going to be an H attached here, which energistically is not possible at all.
Wait, it'd be attached to the thing in the carboxylic acid group, right?
It would be attached to the double bond of oxygen. You'd probably see something like this. This bond becomes single, and this becomes a plus. That's most likely what's going to happen. Like I said, not very likely. It's not, well, actually, this would still be double bonded. The idea of having an acid or an H plus attached like this, it just doesn't make very much sense. And it would have to be very extreme conditions in order for this very unstable molecule to exist. So that's why, okay, hold on. There we are. So that's why I'm gonna put, hold on. I'm gonna put CH3CO. I'm gonna rewrite the way we put this. I'm gonna put this right here. CH3COH2 plus, because that's the way it actually looks, right? We have CH3COH2, and there's two of these, plus. I'm gonna separate the plus real quick because it's OH2. Anyway, that would be the theoretical conjugate acid of acetic acid. And knowing that acetic acid is a weak acid, what would you predict this conjugate acid to be? Would it be a strong acid, weak base, strong base? What do you guys think?
Strong acid?
Strong acid, definitely. because if this is already a weak acid, then adding this unstable H plus means that this H plus is going to be so likely to leave the molecules. And this molecule is just so ready to separate into H plus and acetic acid that it's probably going to do it. It's going to be very acidic. But anyway, this now gives us a new measurement. This is now not an H2O solution. It's not an aqueous solution. It's now a acetic acid solution. So what would actually happen here is most likely HCl is now going to be considered a weak acid. I'm going to let that sink in for a little bit. HCl here is going to be a weak acid. Let me adjust this. All right. And then HBr, probably also weak acid, I'm guessing. And then HI. This is not the scale, by the way, but the reason why these are weak acid is something something known as the leveling effect, where basically the leveling effect says that depending on, well, basically the acidity of a certain compound in a solution depends on the relative acidities between that compound and the solution it's in. So if I have a more acidic solution, such as acetic acid instead of water, the acids that you put in there are going to come off less acidic. And what I mean by come off less acidic means that they don't separate as easily into H plus and Cl minus. Think about it, it does make sense, right? Because the acetic acid itself is separating so readily, you're going to have a lot of H plus in that solution by itself already. So by equilibrium, it wouldn't be favorable to add so much more. So therefore, HCl is not going to separate as easily in acetic acid solution than it is in water. Any questions? Specifically about the idea, like I feel like the idea that why would it not separate as easily? I think that's probably going to be a little bit unclear, because we would need an equilibrium understanding about that. So with that, I guess the easiest way to put it would be if you have like a lot of a certain compound. So say you have a lot of H plus floating around, adding more H plus, what's going to happen is that the other H plus is going to then, because you have so much more, you're going to then react with other compounds. So for example, if it's in water, you're going to form H3O plus, things like that, to basically take out the H plus. Or you might start reacting with other compounds in the water. Like for example, if you have a lot of H plus, you theoretically could make KOH precipitate in solution. It's very hard because KOH is so soluble. But if you have, what am I saying? So basically, when you have a lot of H plus, then it's like having, let's say, for example, HCl separates the H plus and Cl minus. Having a lot of H plus means you're more likely to form Cl minus, HCl, because you have so many more H pluses moving around. Any Cl minus is now more likely to hit an H plus and have enough energy to react. I'm not sure if that made it clearer. Any questions?
Not really.
Not really? All right. So Angelina, you say not really. Can you explain the leveling effect to me?
Repeat.
Can you explain the leveling effect to me then?
Oh, the thing with the wait, sorry. The, the thing with the equilibrium thing you just
Yeah.
mentioned? Oh, well, you said that so if CH 3CO OH2 plus is dissociating really quickly and adding a lot of H pluses, it doesn't make sense for the other acids to dissociate and make more H plus. Sorry, wait.
Yeah, no problem. Yeah, you pretty much got it, I think. So basically,
Yeah.
if a solution already has so many H pluses, mainly from the acetic acid, if you have an acetic acid solution, the acetic acid is releasing H plus, right? So you're gonna have a very high concentration of H plus. And the fact that you have so much means that if you add more to it, then the H plus is all gonna react with other molecules and basically be removed from solution. So basically, you're not gonna be separating so easily. Like HCl is not going to be separating into H plus so easily. So it becomes less acidic in acetic acid solution relative to water solution, where water is not as acidic as acetic acid. So it's not going to have that, and therefore HCl is going to be relatively stronger in water. All right, we kind of went on a pretty big tangent, but that's leveling effect. It is kind of an important concept. Does come up once in a while. And we also talked about naming conventions with C2, H4, O2, things like that. Anyway, the effect also works the opposite way. So for example, if you have a solution of ammonia, if you have a NH3 liquid, you have like a beaker full of ammonia, then if you put like water in there, water is going to be acidic in ammonia. It's going to be a weak acid in ammonia. Does that make sense? Why it would be able to
Yes.
do that? Yeah, because water would be more likely to separate in something that's basic. Okay. Anyway, I think that's enough for now, at least about acids and bases. Real quick, I think we should talk about K, which we talked about like probably a few weeks ago, but K. Can anyone remind me what K is? What does it stand for? What does it mean?
Isn't it a constant?
Yeah, it's a constant. It's what's called the equilibrium constant. So for each reaction, there's going to be an equilibrium constant, and that's constant for that reaction. And the only things that would change an equilibrium reaction are like temperature, potentially pressure, things like that. But the concentrations of compounds themselves never changes the equilibrium. And if I have a reaction, I'm just going to write a very simple reaction real quick. CH4 plus 2O2 goes to CO2 plus 2H2O, for example. The way I'd find the equilibrium expression for this equation is I put the products on the numerator and then the reactants on the denominator, and then the coefficient becomes the power. So what I mean is at the top on the numerator, this is going to be the concentration of CO2. And since the coefficient on CO2 is 1, I'm just going to keep it power 1, multiplied by H2O, the concentration of H2O, squared, because there's a coefficient of 2. And then on the denominator, that's going to be CH4, 1, because coefficient of 1, and then O2 squared. Kind of like that. This is what's called Kc, which is a little bit different because notice that everything's in concentrations. That's why it's going to be called Kc. Kc. Another version of K would be Kp, which I think is more applicable in this case because Kp is dependent on pressures. So it's going to be an equilibrium expression, but for pressure. So it's going to be pressure of CO2, pressure sub CO2, multiplied by pressure of H2O squared. And then here is pressure of CH4, and then pressure of O2 squared. This water that we're talking about here is not going to be liquid, it's going to be gaseous. So all these compounds are gases and therefore they can all have measurable pressures. And this would be our equilibrium expression. Kc and Kp just stand for equilibrium constants. That's a good question, Larry. So this just means equilibrium equilibrium constant. Each reaction has a certain number. How can H2O be a gas?
Water
Steam,
vapor.
water vapor. Yeah, that's a good example. So H2O can be a gas. H2O solid is ice. H2O gas is like steam, water vapor.
I have a question.
Yeah.
This might be kind of dumb, but what about KEQ? Like so.
KEQ. Yes. KEQ is basically what K is. It just means K equilibrium. So it means the same thing. Yeah.
Okay.
There's all different kinds of, like Ka, for example, is an acid separation expression. Kb, these are ones we've talked about. There's going to be one called KSP, which is for solubility product, which comes into play when you're talking about solubility. How do you find these constants? Yes, first of all, they are constants. How you find these constants is experimental. So you would conduct this reaction, collect data about your reactants and your products, and figure out where it equilibrates, where it stabilizes, and then find your constant from there. And then afterwards, you can use that constant for any other kind of reaction that you want to predict. So what's the equation for? It's to relate different concentrations. So basically at equilibrium, let's say like I have a certain amount of CO2 and H2O and CH4, and I'm looking for the concentration of O2, then what I'd be able to do is plug those numbers into this equation and find O2. Or for example, if I start out with CO2, some amount of CO2, some amount of H2O, I want to find what their values would be at equilibrium, then I would be able to use the K expression to do that. So that's what the equilibrium equations are for. They have a lot of predicting power, and that's what we're going to get to right now when we get to some problems. All right, so what I want to do is first I'm going to start with just a problem of my own. I do
Wait,
have some, yeah.
we did this before once, right? Isn't it the thing where you only care about the aqueous solution or something?
But yeah, that's another detail that I should mention. Yeah, you for equilibrium expressions, you only look at aqueous and you only look at gaseous. Those two are the ones you only look at. So let's say you produce H2O liquid in a certain reaction, then you don't include that in your expression. Liquids and solids are not included in equilibrium expressions. They behave differently. The fact that they exist is enough for a reaction to go. They don't really impact. They don't really impact equilibrium. Yeah, that's a good point. Thanks for bringing that up, Angelina. Let me quickly just write out a question though, for us to start out with. Let's say I have a 0.10 molar HC3, I'll call CH3COOH. We'll start with that. I have a 1.0 molar CH3COOH solution. And I want to find out what its pH is. All right, everyone understand the question. CH3COOH, we know it's 0.10 molar solution, and we want to find its pH. First, we have to write out the acid-base equation for COOH. In this case, it's going to be an acid equation. Anyone remember what an acid equation is?
Do you like represent it as the like H plus the rest of the compound or something?
H plus the rest of the compound, yes. And the rest of the compound would be what's called the conjugate base, right? Right, if you remove the H plus, you have your conjugate base. So I'm gonna write that as H plus conjugate base. Anyone want to give that to me? What's the conjugate base for this?
CH3COO minus.
CH3COO minus. The CH4COOH, that would be leaning toward conjugate acid. You'd be adding an H plus. So removing an H plus would give you the conjugate base. Yeah. So this would be our expression. All right, and I'm gonna also denote that these are all aqueous parts, all in water. I'm put that down there. Usually you'd put it next to it, but yeah. So now we can write out our K expression, our equilibrium expression. In this case, since we're dealing with acid, we can also call it Ka or KEQ. These would all be okay. All right, so let's think about how we made this again. It's going to be reactants on the denominator, products on the numerator. So what are our products here? Pretty simple
Oh.
question, no need to overthink.
H plus and CH3COO minus.
Yes, so we're going to have concentration of H plus multiplied by CH3COO minus. Do I need a power on any of these? Do I need an exponent?
No,
No, why not?
because there's no coefficients.
No coefficients, yeah. Or
And
coefficient of 1
Or
would
yeah,
be.
coefficient of it, 1. And,
Yeah, so this would be to the first power, and that's the thing.
wouldn't
All right.
it need to be divided by the concentration of the reactant too?
Yeah. So what would that be?
So it would be the concentration of, so just temp 0.1.
Yeah, the way you got that was basically you look for the concentration of CH3COOH, right?
Yeah.
All right. Right now we got to write out the expression first before we start plugging stuff in. Yes, we have this. All right, so this is going to be our equation essentially. And like I said, like I mentioned before, the Ka is a value we know. We measure it. Usually in this kind of question, they're going to give you the Ka. And I'll give it to you guys right now. It's a very famous Ka, 1.8 times 10 to the negative fifth. That's just the value of it. So we have this equation. We've written our equilibrium expression. That's going to be our first step. Now we're going to talk about what to do with this thing. So where can we find the recordings for these classes? Should be posted on the Logistem website, Larry. I'm going to check in with Zara to see if the most recent ones have been posted, but I'll check in with her, then I can always get it to you directly. So yeah. Anyway, let's work with this equation. So now I'm just gonna ask a very simple kind of question. You guys probably gonna feel like it's very simple. Let's say one molecule of acetic acid is broken up in this reaction. One molecule reacts. How much H plus is formed from that one molecule?
1.
One. And then what about the conjugate base? How much of that?
Also 1.
Also one, right? So basically, I'm going to change the question a little bit. Let's say I have X molecules. Oh, Larry, why is it one? All right, so if one of this molecule breaks apart, just think about CH3COOH breaks apart. You have H plus, you have CH3COO minus. One molecule of reactant would then break apart to one molecule of product and one molecule of the other product. Does that make sense, Larry?
Yeah.
Why doesn't it keep on breaking apart? What part would break apart here? When you say why doesn't it keep on breaking apart? The breaking apart of the acetate ion would be a different reaction. So we're talking about just this one reaction here, where the acetic acid breaks apart. Yeah, you got it. So now I'm gonna change the question a little bit. Is it? No, it's not always one. Well, there'll be a 1-to-1 ratio. So if one molecule of acetic acid breaks apart, then you have one molecule of each product. If you have two molecules of reactant, then you'll have one molecule. Then you have two molecules of each product, so on and so forth. Sorry guys, I'm answering Larry's questions. He's typing to me through private message in the chat. In case you guys are confused. Does it make sense, Larry? Yeah, it's a ratio. All right. So changing the question a little bit. It's still gonna be the same question though. Let's say I have X molecules of acetic acid, X molecules of reactant, how many H plus will I have?
X.
X, and then same thing with the base.
Yeah.
And then if I have X moles of reactant,
It would be the same thing.
X moles, yes. Okay, so we can express this in our Ka reaction. So basically, actually, let me do it the standard way that most people do. I'm gonna build what's called a rice table, and I'll explain what that means. So I'm gonna just quickly make it. All right, and this is gonna be, well, this is not really a traditional rice table, but it is okay. I, C, E. So basically, what I, C, and E stand for is initial, change, and end. So basically, the initial concentration we have, the change in concentration, and then the end. So this all makes sense in like 2 minutes. So just give me a sec as I fill this out. CH3COOH. That's supposed to be in the box. H plus, and then
Excuse me.
yeah, what's up?
I have to leave early. I have some medical emergency, I guess I could call it.
Yeah, no problem. Hope everything's
Sorry.
okay.
Thank you.
Yeah, we'll have the recording up
All right.
soon.
Bye.
Yeah, bye. No problem. Uh, anyway, I'm filling out this table. We have the compounds right here. So I can technically put R here. R is supposed to stand for reaction, but I didn't really write out the reaction. I have it up here, so I don't really need to. But anyway, we have our compounds. What is the initial concentration of acetic acid? This should be given in the problem.
0.1.
0.10 molar, yeah. What right stands for is, yeah, we have reaction, initial, change, end. So R, typically you would write the reaction at the top and label it R, and then you have ICE going down. I didn't really do that because the reaction is up here. I already wrote it. So this is technically an ice table, not a rice table, but it's okay. This is just a basic idea. It's just meant to be like a intuitive trick. Anyway, moving on to the harder question, because the concentration of acetic acid, that's given to us. What about H plus? What is the concentration of H plus initially?
It would be the same as the acetic acid, right? Wait, no, I'm wrong.
No?
It, do you know how much of H plus there is? Like
You
the
do. It's not given in the problem, but you do know it.
so you would multiply by the amount of you would multiply the number of moles or find the number of moles with the molarity of the initial compound.
You're thinking about like if they actually gave you the information. I'll answer this one, and then it'll make a lot of sense. The initial concentration of H plus is going to be 0 molar. What do I mean by that? It means that when we start out with a solution of 1.0 molar, a 0.10 molar acetic acid, that's all acetic acid. At least if you think about the second I put in the acetic acid into the water, it hasn't separated yet, right? So we're going to start out with 0
Oh,
H pluses, right?
yeah.
Yeah. So of course that's not true. We start out with 10 to the negative 7th H pluses, and that's because water separates by itself. Remember, water separates into H plus and OH minus. So we do have some tiny bit of H plus being separated, but it's so extremely small compared to like 0.1 that we don't even consider it. At least we can estimate it to be 0. Anyway, H plus is 0. Knowing H plus is 0, can you tell me what acetate is? The
0.
0 as well. Larry, you mentioned 0.1. 0. Yeah, you get why it's 0, right? Because you also start out with no conjugate base. You start out with none of it before you separate. Yes, so it's going to be 0 molar as well. All right, for the change part, it's always going to be the same thing. Basically, in this case, we have a lot of acetic acid, right? So I think it should be pretty obvious that this reaction, what goes on is that it separates. So basically, we're going to lose acetic acid. So what I'm going to put here is minus X. Basically, I'm going to lose some amount of acetic acid. Some amount of acetic acid is going to break apart into my products. All right. So what will I put for the change in H plus? Knowing that X amount of acetic acid is breaking apart, how much H will I be getting? How much will H change?
It would be it would change by positive X.
Plus X, yes. So yeah, plus X, exactly there. So acetic acid, we're losing X, but from that X, from these lost molecules, they're not lost, right? They're broken apart into new molecules, specifically H plus and H3COO plus, minus. So we're also going to have plus X down here. Basically, minus X of acetic acid, but plus X both for the product. All right, for N, for E, we basically just put together initial plus change. So what would that be for my acetic acid?
It would be 0.1 plus X or minus X. Sorry.
Minus X, yeah. So 0.1 molar minus X, yeah. Next one should be pretty easy. X, as Larry said, exactly. And then this one X as well.
Yeah.
All right, so this is the idea of the rice table. And what I'm gonna do essentially is, well, first I'm gonna move this table over. Dang it, it doesn't move together. So annoying. Hold up, give me one sec. Here we are. I'm gonna move that over. And I'm going to rewrite my Ka expression, but this time, what I'm gonna do is I'm gonna plug in the things I have for E, for N. So I'm gonna plug in H plus. What is my H plus value for N? So in this column, what do I have for H plus?
It's X.
X, yeah. So basically my final concentration for hydrogen ions, what I am eventually left with is X. Oops, I drew my own screen. Um, what about for acetate? What am I left with?
Uh, 0.1 or acetate.
Acetate ion.
Wait, the reactant you mean?
The product,
Oh,
acetate.
it's also X, so it's X squared.
X squared, yes. Larry's jumping ahead. That's great. Uh, and Larry, as you pointed out, the denominator would have 0.1 minus X. We're just plugging in the end, right? And this would be equal to 1.8 times 10 to the negative 5, our Ka expression. And as you guys could probably see, this works out to be a quadratic, something you could probably solve. And you find a value for X from this. And our X would then be our concentration of hydrogen ions. And then to find the pH, you of course just take the negative log of H plus. Remember we talked about pH equal to negative log of concentration of H plus. And yeah, the problem's solved just like that. One point before I lose track of it is there's a shortcut you could do with this. And that is you can take away this minus X term. And let me explain more. So uh, first, actually, before we do that, let us try working out the solution without taking away the minus X term. Now, I don't know about you guys, but my calculator has a equation solver functionality. So I'm quickly just going to use that instead of wasting a lot of time trying to solve the quadratic myself. And I'll tell you guys a value real quick. what I got is x is 10 to the, okay, let me, x is 1.33 times 10 to the negative third. Basically very small. Now let's think about this term again. Let's think about this term right here. If x is 0.00133 or 1.33 times 10 to the negative third, is it making a big impact on 0.1?
No.
No, it's taking a very small chunk away from that. So if I were to replace this with just 0.1, of course, x is going to be different, but what actually is going to happen is that it's not going to be different by that much. So what we can do is actually simplify this equation by making this small error, in a sense, this small assumption, and that makes our equation something that we can solve in our head. I just calculated it right now, and what I got was 1.34 times 10 to the negative third for our value of x. So 1.33 times 10 to the negative third now changed to 1.34. That is like less than 1% error.
Yeah.
And that is something we can accept. So usually when you're doing these acid-base questions, you can simplify the question by taking away that minus x. Of course, you can always do it and you'll always be more accurate, but it's just so much more work, especially on a test situation. You don't have that luxury time to work through. So that's a small simplification you can do. I do want to caution though about doing that. When you're dealing with something like, let's say, for example, there was a theoretical acid that was 1 times 10 to the negative 1 for its Ka. All right, just imagine that. The error of taking away the minus x is going to be much, much larger, and it's going to be an error that's irredeemable to an extent. Let me just do the calculations real quick. So for x, I got 0.1 for when you don't account for the numerators, the denominators minus x. But if you do account for it, what you get, hold on, let me try this again. What you do get is 0.061 or 0.062. So when you account for the minus x with an acid of 10 to the negative 1, you get 6.2 times 10 to the negative 2. But then if you don't account for the minus x at the denominator, you get 0.1. Now that's going to be a much larger error. So usually when you do this assumption, you're going to need to have an acid that is kind of weak. So it's got to be probably at least like 10 to the negative third in negative magnitude in order for this assumption to be potentially valid. And then it also factors in this component, your initial acid. How much of that do you have? If you have a lot more, then the assumption is more valid. But let's say I had like a 0.00001 molar solution. This minus x is going to be relative to this much bigger, and therefore if I take it out, it's going to be quite a bit of error going into it. So the assumption works, but only in certain circumstances, basically large amounts of acid, small amounts of a small Ka. Now it sounds like a lot of specification, but it does work out quite a bit and quite often. All right. So basically you can disregard x when x is small. Yes, you can disregard x when it's small compared to the 0.1 or your initial acid, and also when it's small, like when your Ka is small. Why does this work only in chemistry and not in math? Because chemistry, it's okay to have like 1% error. That's okay. Math is the art of being exact in a sense. It's the art of doing stuff, doing calculations. And therefore, if you're doing assumptions in your calculations, it kind of defeats the purpose. So that's why. But anyway, um, I'm gonna quickly type up another example question for us to consider. Yeah, we got like 10 minutes left. I don't think this is a perfect time to pull out a harder question. So, um, let us say I have an acid H. Let me think. What's a good weak acid? Ah, let's say I have HF. HF is also going to be a weak acid. Uh, is HF a good example? Maybe this is a better example. Hold on, let me check real quick. Oh yeah, this is a better example. All right. Okay, no more HF. Let us say we have HNO2. This is going to be weak acid. Ka equal to 4.5 times 10 to the negative fourth. Hold on. Larry, your question is, why can't we say it's just 1 plus or minus infinity for... Okay, no, I'm not taking troll comments. That's not acceptable. Anyway, back on this. Ka equals fraction. Can you guys give me the equilibrium expression? Well, first, can you guys give me the acid dissociation equation? Essentially, H2O splitting up. What is that equation? Yes.
Can you repeat that? Sorry.
All right, so H2O, HNO2 acting as an acid. We can write that as an equation, right? What would that
Yeah.
equation be?
Um, you mean like how when it splits apart
Yeah,
into, so
yeah.
it'll be H plus H 2NO minus, right?
2NO minus? How does that work?
No, NO. Wait, no, just NO2. Sorry,
NO2.
NO2 minus, not
Yeah,
2.
so how would I state this reaction? What would be on my left side?
So left side would be HNO2.
HNO2, okay. And then that would be our reactant. So then that would go to what next?
Yeah.
So what would be our product?
um, the product would be H plus and NO2 minus.
H plus and NO2 minus, yeah. So this is going to be our acid statements. This is something you guys are going to need if you're looking to do like AP or USNCO. Uh, being able to write these pretty easily is going to be kind of important. So it's good to get some practice now. HNO2 would separate into H plus and NO2 minus. All right. So how can we state our Ka? So Larry, you mentioned H plus NO2 minus. There needs to be a minus on that, just saying. That goes to HNO2. That's like the opposite of the acid equation. You just want to flip that. Okay. Starting with HNO2, breaking apart. Anyway, what's our Ka statement? Knowing our equation. We have this.
Yeah, so it would be H plus times the concentration of H plus times NO2 minus
Yeah.
divided by the concentration of HNO2.
Divided by concentration of HNO2. That sounds good to me. And we can set that equal to, hold up, set that equal to our Ka. All right. So this is going to follow the same pattern as we did before with the x's and stuff. So I'm wondering, can anyone tell me how we can simplify this down? Essentially plugging in x's, all that stuff.
So it would be
On the numerator, what would we have?
It would be X plus X.
X plus X?
Yeah, it would be X for both H plus and NO2.
Yeah. So would that be X plus X? Or would it be something else?
It would be X squared.
X squared, yeah. X squared. And then denominator, Larry, you're giving that to us. The 4.5 though, this might be a point of confusion. 4.5 is connected to the Ka. I actually never gave a concentration for this acid, and that's my bad. I didn't fully state the question, but I'm just gonna set the initial concentration of acid to be 0.01. Set it like that, 0.01 m. So we're gonna start with this, and then minus x, as Larry, you mentioned. All right, and that's going to be equal to our 4.5 times 10 to the negative fourth. All right, now something I want to ask you guys. Do you think it would make sense to remove minus x here?
Yeah, because it's really small, right?
Kinda, but is it really small enough, do you think? Larry's
Uh,
saying no. What do you think, Amos?
I'm not sure now.
Yeah, not sure. Okay, that's something that honestly, it's probably on me. I forgot to mention it. It's an important point. I did say that you sometimes are able to remove, sometimes not. I think a good metric for when you're able to remove is if the power of 10 between these two differs by more than 3. I think that's probably the safest. So in this case, you have 10 to the negative fourth, and in this case, you have 10 to the negative second. Differs by 2. Probably you want to keep the minus x. Let's say this is 1 molar, for example. This would be power of 0, power of 4. That would be different enough, and you can easily make the assumption. If this k were 10 to the negative 6, and this were 10 to the negative second, then you can make the assumption. So basically just look at the powers of 10 with your Ka and with your, and with your initial acid concentration. All right. Good that we mentioned that. So in this case, we wouldn't make the assumption. And basically the last step we have to do is just solve out for x.
Look,
Any questions?
no.
All right. I don't think we need to solve out for x because that's just quadratics,
Yeah.
which is just plugging numbers. That's not a problem. Anyway, so that's acids. Maybe trying. Is this stuff covered in AP Bio or AP Chem? In AP Bio, you'll have to know like some very, very basic chemistry things. This stuff is AP Chem for sure, so not AP Bio. I don't see this stuff happening in AP Bio. I did take AP Bio, so yeah, I know for sure. No, we don't cover this stuff. Uh, is it hard? Is AP Chem hard or AP Bio hard? Which one?
They're both.
Both. Okay. I'd say it's not the easiest AP. Like if you think about like AP psychology or something, most people would say it's easier. AP physics, which physics? Physics 1, 2, or C? 1. AP physics 1. The thing with that is I've never taken one, so I'm not sure. But from what I heard about it, I personally think that these are easier, slightly easier. Mainly because one has, I know it has a lot of explanation, very nitty gritty experiment designs, whatnot. It's a little more similar to AP Bio in that sense. AP Bio has long FRQs I have to write a lot about, being very specific. It's just different content. So if you're not a bio person, it will be harder for you. If you are a bio person, it'll be way easier for you. Depends on what
Um,
subject.
I took both AP Physics C's, and I thought I got fours on both of them. So I
Mhm.
think they're like they're decently difficult, but I think that they're easier than Chem, AP
You
Chem.
think they're easier than Chem? Okay.
Yeah.
Um, personally, I thought chem was easier, but that's just me. I'm a chem guy. What can I say? But I think mainly it's just knowing the stuff. It's not going to be an easy AP, no matter how you dice it. There is a lot of content, but if you're a science guy, I think it'll work out. What grade am I in? I'm a senior currently. So I'm a senior at Montgomery High School. Uh, yeah, Larry, you weren't around when I used to give my introductions, but I'll give a quick introduction for you. I'm a senior at Montgomery High School. Uh, in terms of my chem and bio background, I've taken both tests, both gotten fives. I've also taken physics C, gotten fives as well. Um, and USNCO, I'm top 50 placement, high honors. And with USABO Bio Olympiad, I am top 400 semifinalist. That's a little bit about me. Um, Anyway, that more or less wraps up our time. But what I wanted to do real quick, if you guys are nice enough to, yeah, I did compete in, yeah, both of those. I did not get into the national team, no. That is top 20. I was top 50, just a little shy. I probably was very close. I think I studied my ass off for that thing. But anyway, close enough for my enjoyment and my happiness. What I wanted to do real quick is bring up a real quick question. Um, just to give you guys a bit of a preview, I think that right there, we never actually got to these questions, but I think that's completely fine. It's best to take these things a little slower. Um, not good to rush things with it. This is an example of something you might encounter on USNCO or AP. This I think kind of falls into both categories. Um, In this case, I'm just gonna give a quick overview of the question. We're not gonna do this right now. You're given Ka, you're given the acid you're working with, so you can write out your equilibrium expression. And then you have this, which is your conjugate base. NaF is just a source of your conjugate base, essentially. So you're gonna start out not just with the initial of one, you're gonna start out with two compounds having initial quantities. And then you do the plus X minus X as necessary. Another thing that I think is interesting about the question is that these acids, they actually get diluted. The acid and the conjugate base both get diluted by themselves. So you have to calculate the new concentration. Anyway, this is just kind of like a step above of what we did, but still same principles. You find the equilibrium expression, you solve out for X, and then you find your pH from there. Anyway, a little preview of what we might do next week, but I'm also thinking next week we should probably talk about some bio in case. Are you guys more interested in bio or chemistry when you're coming here? So I can get a sense of how I should adjust what we
Chemistry.
talk about.
Taking chemistry, AP chemistry right now.
Yeah, you're a chem guy, Larry. Are you here for the bio or for the chem or for both? Both is fine. Okay. I know Angelina prefers bio, so I'll just kind of alternate. So next week we might talk about like biochem or bio. No, we'll see how it is. I'm a freshman of a B in bio. Uh, um, no, you got it, dude. Let's talk about some bio next week. But it will be like biochem stuff, so it's not gonna be like useless aimless. Uh,
Okay.
hopefully you can stop by. Anyway, um, that kind of wraps us up for today. And hopefully we went over some more acid stuff, kind of reviewed, but also built on our knowledge a little bit with some acid questions. And yeah, we'll pick up the discussion next week. So we'll see you guys then. Bye bye.
All right.